Oké, laten we beginnen. Goedemorgen allemaal. Good morning everyone. Mijn naam is Raymond de Jong. Ik ben een Senior Technical Product Manager bij VMware, bij de Network and Security Business Unit. Gezien de remote sessie ben ik alsnog uitgenodigd voor een sessie over vSphere met Tanzu. En dan met name voor NSXT. Ik heb begrepen dat deze sessie opgenomen gaat worden. Dat betekent dat ik ook in het Engels ga presenteren, omdat ik hem dan de opname meerdere malen kan delen over meerdere platformen over de wereld. Ik hoop dat dat geen probleem is. Voel je vrij om vragen te stellen via de chat of na de sessie. Ik heb heel veel content, maar ik hoop wel aan het einde van de sessie vragen te kunnen beantwoorden. En ik kan ook altijd nog even in de sessie blijven, zodat er eventueel alsnog vragen beantwoord kunnen worden. Dus laten we beginnen. First, a disclaimer. We all know vSphere 703 has recently been removed due to some issues. That also means that some features I'm going to present in this session are still subject to change. I did a similar presentation at VMworld when it was future, and now it's past. But in that sense, the features I'm presenting will not be changed as far as I know. But still, this disclaimer is in place to keep in mind that some things might change with the release of vSphere 703. So with that out of the way, the agenda for today, we'll start with vSphere with Tanzu overview and the topology and features we support. After which we're going to do a deep dive in routing, security, load balancing, and edge clusters to successfully design and scale vSphere with Tanzu and NSXT, and giving you options and opportunities to adapt the topology running on NSXT to meet your enterprise requirements. So first, starting with the overview, vSphere with Tanzu, as we all know, transforms a common vSphere cluster managed by vCenter, managed by a vAdmin in a supervisor cluster, which means that we are going to install a Kubernetes control plane on your cluster, which a DevOps engineer can interact with and create resources on for their development teams. This means we can create pods, TKG clusters, or even VMs using VM operator. And this construct is something we call a supervisor Kubernetes cluster, or supervisor cluster in short. So every time I say a supervisor cluster, this means a single vSphere cluster transformed in a Kubernetes cluster to be able to host native vSphere pods, VMs deployed using kubectl, or TKG clusters deployed on that cluster. And this enables us to, from a DevOps engineer perspective, to use kubectl to create services on top of the namespaces in a supervisor cluster, whereas a vAdmin can manage and monitor those resources with the tools they are used to. So in your SDDC, you can have one or more supervisor cluster, which can have multiple namespaces in which you can create vSphere pods. Using the VM operator, you can use kubectl to create VMs, and you can use Tanzu Kubernetes clusters to deploy resources inside those clusters. And this means you can have multiple topologies side by side, used by different teams in a similar way, and that's very easy and flexible for everyone to use. Now for vSphere with Tanzu with NSXT, this brings a number of features which adds value and gives flexibility to your environment to use vSphere with Tanzu. Every time we talk about a supervisor cluster in context with NSXT, we need to think about vSphere host and edge clusters in NSXT as resources for networking services, specifically edge clusters. And that will be common in this presentation as well, because edge clusters are more or less a resource pool for your networking services you are going to consume with vSphere with Tanzu. And now, when I talk about network services, we need to think about firewalling, netting, load balancing. All those resources will be bound to a tier 1 gateway in NSX and will be run on an edge cluster. So looking forward at the features is 5 main categories of features in vSphere with Tanzu with NSXT. First of all, the inbuilt IPAM address management, segmented networking layer 2 and layer 3, firewall isolation through distributed firewall and the north-south gateway firewall, load balancing ingress, and visibility day 2 ops. So when you use a supervisor cluster with NSXT, NSXT manager takes care of IP address assignment of all the networks you create when you create a supervisor cluster. When you go through the wizard to transform a vSphere cluster as a supervisor cluster, you need to specify CIDR ranges, which then will be managed through NSXT and automatically be allocated to the resources in your supervisor cluster. And those ranges are ranges for your pods, for your services, for ingress and egress. I will talk a bit more about that later. Topology and network segmentation using NSXT means that for every namespace you create in a supervisor cluster, you will get a dedicated tier 1 gateway. In each namespace, you can have one or more segments associated with that namespace, meaning that if you create a namespace, it gets a tier 1 and one clean empty segment. And then you can create vSphere pods, TKG clusters, or VMs using the VM operator. When you create those resources, they will be created on dedicated segments and automatically be connected to a tier 1 gateway for that namespace. They also will be assigned automatically a subnet CIDR and a gateway IP address to make routing possible. If we look at routing, obviously we support all kinds of routing north-south, static and dynamic, connecting to your physical network. And obviously every namespace created in a supervisor cluster will be automatically connected to a given tier 0. And the routing in NSX will be automatically plumbed to make sure we have routing towards the tier 0 gateway. And then it's up to you how you want to connect your supervisor cluster to the physical network, of which we are going to talk a bit later as well. A new feature coming in vSphere 703 is the option to enable net or routable pods. So by default, each namespace is netted, meaning that when you create vSphere pods, TKG cluster nodes, etc., all the traffic outbound from the namespace perspective will be source netted to an IP address, uplink IP address, and egress IP on the tier 1 gateway. With vSphere 703, you can also enable routable pods on the cluster or per namespace, of which we're going to talk a bit later as well. And this gives you more flexibility in the type of Kubernetes resources you want to use and how to interact with them using as IP addresses for pods. Security features is obviously about, securing your workloads using the distributed firewall and or securing your namespace on the tier 1 gateway. And each of them have flexibility and considerations we need to take care of. And we're going to deep dive today as well on that topic. And then obviously load balancing features. So at the moment, each namespace gets a dedicated load balancing instance, which will be associated with the tier 1 gateway for that namespace. And it will be a shared load balancer for resources in that namespace. And you can tune and do different things on a load balancer per namespace. We'll talk about that today as well, as it has some considerations and things for scale and flexibility for you to consider. And then visibility and monitoring. Obviously, NSXT has full visibility of every workload running in NSXT, meaning that every namespace will be visible in NSXT. Using the inventory containers page, you can find the namespaces being created on the cluster. You can find the operational status of the cluster, and you can click on all those services and networking components to find out what's being created through NSX and to see even on the interface level what's going on and to monitor traffic going in and out, namespaces and workloads on your supervisor cluster. And it also means we can support tools like troubleshooting tools as traceflow to give full visibility in the path of vSphere pod or TKG nodes to another resource in the NSX environment. So let's now talk a bit more in deeper level about some of those features I mentioned before, starting with routing. If we talk about routing in a supervisor cluster, we need to consider two main components, which is the management network and the workload network. So the management network in NSXT is just, the interaction between vCenter, NSX Manager, and the vSphere hosts. We require a VLAN-backed VDS port group for management components and also to connect the management control plane VM connectivity to. This has to be a routable network to vCenter server, has to be able to reach NSX Manager and the vSphere hosts. Then we need 5 consecutive IP addresses for the supervisor control plane. And we need 5 because 1 is a shared VIP IP address. The subsequent 3 addresses are for the free control plane node VMs. And the 5th IP address is being used for rolling upgrades. So if you're going to upgrade your supervisor cluster, say from version 7.02 to 7.03 from a specific Kubernetes version to another, it will do a rolling upgrade using that 5th IP address. Very important is obviously connectivity also with resources like DNS and NTP. So when you configure an external DNS server, make sure that connectivity works for the supervisor cluster to work as expected. And then the workload network. The workload network encompasses everything I mentioned about the workloads being deployed inside the supervisor cluster, and it's going to be instantiated as the pods IPs, the service IPs for service type cluster IP, ingress and egress for load balancing IPs, and for the source net IPs for each given namespace. These, especially the ingress and egress IP addresses, need to be routable on your network as well, because that's interacting with the physical fabric, maybe the workstation from your DevOps teams, or also interacting with repositories like a Harbor registry or an external image registry. If you look at routing, there are some considerations and requirements. So first of all, the Kubernetes network principle is that pods and nodes are routable within a cluster. In terms of ingress traffic, that will always hit the NSXT load balancer first before being able to reach those workloads inside a namespace. That means that source netting and denetting will happen on the load balancer running on an NSXT edge node. For egress traffic, currently the product uses the same source net IP for workloads in a given namespace, meaning that it's a shared IP for a namespace. So vSphere pods and or TKG nodes with external traffic will use the same source net IP. And if you do TKG clusters and have by default that traffic from TKG clusters will be source netted as well. So that means that you have a source net on a TKG node, after which you will have a source net on your tier 1 gateway as well. And in terms of network side requirements, it's important to understand that you should not have overlapping IP addresses between TKG clusters and supervisor clusters. And between multiple supervisor clusters, take care of not overlapping IP addresses. So, like I mentioned before, each namespace gets a dedicated tier 1 gateway and a segment with, by default, a /28 subnet prefix. You can change that on a cluster level, starting from vSphere 7.03, but by default, this is the configuration. That means that all workloads inside the namespace are hidden from an IP perspective to the outside world. And NSXT takes care automatically of allocating those /28 networks to the segments it requires to create. So when you create a namespace and delete a namespace, NSXT will do the cleanup and the networks will be available for subsequent namespaces again. Very important IP range is the ingress and egress IP allocation. So this is all about, for ingress, for load balancing services for your namespace, and egress for source netting IP for traffic outbound from a namespace perspective. So each namespace, when you create a namespace, gets one IP for egress traffic. That means that at the moment you have that shared IP, and every workload going outbound will originate from that IP in a netted configuration. Then for each namespace, it will be allocated one ingress IP by default to be able to interact with, for example, the TKG cluster, and to be able to reach the Kubernetes control plane on a TKG cluster. And when you create subsequent services of type load balancer, or in case of vSphere pods Ingress, then those will be allocated, if needed, additional IPs for Ingress to be able to host that IP and port combination for that given namespace. NSX and Supervisor Cluster will take care of tracking those IPs and allocating those IPs to namespaces. And when you remove those resources, those IPs will become available again. In terms of north-south routing to your physical network for small deployments of proof of concepts, we recommend to leverage the Proxy Art feature in NSXT, which gives you the opportunity to proxy Art requests for IP addresses hosted on the loopbacks on tier 0 and tier 1 gateways to your physical network, which is only supported at the moment in active standby. But this has the benefit of, being able to quickly create a supervisor cluster without having you to create some kind of static routes or dynamic routing on the physical network. For medium deployments or deployments which are not able to leverage dynamic routing, obviously you can use static routing configuration, and then you can set up an HA VIP on your tier 0 gateway to attract traffic from the physical network, and obviously create routes as a default gateway towards the physical network. And then make sure, obviously, on your physical network to point all the ingress and egress networks towards that tier 0 HA VIP to make sure that works. Static routing with HA VIP requires static standby, active standby tier 0 configuration. So keep that in mind. And finally, and the best option and the most flexible option, and also the best performant option, is using dynamic routing, setting up your tier 0 gateway as an active router, interacting with your physical network through either eBGP, IBGP, or OSPF, and advertising routes, ingress routes, egress routes, or in case of routable ports, all those routes towards the physical network automatically. Given the fact that you can use active for dynamic routing topology, means that you have better performance in terms of scale. So you can scale out easily the number of edge nodes you require. So you can get more throughput for your supervisor cluster. And in terms of availability, this has benefits because if you use ECMP, in case of a failure of an edge node, that means that only part of the flows will be affected. And you can leverage mechanisms like BFD to quickly detect failures on the physical network or between an edge node and a tier 0 gateway towards a given physical network switch, fiber, top of rack, to quickly redirect traffic to another router. In large deployments, you can even consider bare metal edge nodes, because bare metal edge nodes have obviously superior performance, but also you can set sub-second BFD timers to even be faster detecting failures on the network. And now we're going to move to some new features being introduced in vSphere 7.0.3. First, the net or routable pods. So by default, like I mentioned before, a given namespace will be netted by default, but you can also configure on the cluster level or on a namespace level the option to use routable pods. So routable pods means that the network CIDR you create for a supervisor cluster, each segment being created in a namespace will be advertised to the physical network. Obviously, you can summarize and aggregate those networks on your tier 0 gateway for advertisement reasons and to keep your BGP and OSPF table clean. What's important is that you make sure that those networks are routable, do not overlap with other networks, and in case of multiple supervisor clusters, that the allocation of those ranges are unique and not overlapping. Also, TKG clusters themselves can be set up using as a routable pods, meaning that there will be no source netting on a TKG node, and they will directly communicate with the network. Additional layer here is obviously that they should not overlap IP addresses from between a TKG cluster and a supervisor cluster, and between supervisor clusters and TKG clusters. On the cluster level, you can also configure either a tier 0 or tier 0 VRF, which means that for a given supervisor cluster, you can connect it to a specific tier 0 or tier 0 VRF. So in this diagram, we see two supervisor clusters. And in this case, each supervisor cluster is connected to a specific tier 0 VRF. And this gives obviously improved separation, traffic engineering capabilities, or multi-tenancy options in your design. Then you can also configure from vSphere 7.0.3 on the cluster level the namespace subnet prefix. So in previous versions, the subnet prefix was always /28, but on a cluster level, you can make it either /29 or /26, 27, whatever you need, compared depending on the IP addressing needs and requirements for your development teams to operate. And this is obviously about how many nodes, TKG nodes, how many vSphere pods you expect in a namespace. And per cluster level, if you have, let's say, more than 14 TKG nodes in a given namespace all the time, it makes sense to make that subnet prefix a bit larger. So how it looks in the UI, you can, when you create the supervisor cluster, the arrow points to the net mode. By default, it's enabled. And the two boxes highlight the tier 0 gateway you can select. So that points either to a tier 0 or tier 0 VRF. And the subnet prefix you can configure. Then on the namespace level, there are some 5 things you can override compared to the cluster settings. You can set and override net or routable pods, the tier 0 or tier 0 VRF selection, namespace prefix configuration, and the Ingress and Egress cider. So this means that when you create a supervisor cluster, you can override the namespace configuration for net and routable pods. So this means that, for example, you create your supervising cluster by default using net, but there may be a namespace which has requirements for routable pods, and you can override the cluster settings on the namespace level and configure that namespace for routable pods. Again, the same considerations and advice counts here, as I said earlier. The networks will be advertised to the tier 0, and the tier 0 will advertise them using BGP, for example, to the physical network. So you need to be able to route those IPs and make sure there's no overlapping. And then on the namespace level, you can also override the cluster settings, which enables you to select on a namespace level the connectivity to a given tier 0 or tier 0 VRF. So in this diagram, we have 2 supervisor clusters. The supervisor cluster on the left has namespaces configured, and in this case, each namespace connects to a dedicated tier 0 VRF. So this is a clear multi-tenant example where each namespace maps to a tier 1 gateway and connects to a dedicated tier 0 VRF on the tier 0. But you can also create a supervisor cluster and create multiple tier 0s and have namespaces connected to a specific tier 0. And this is perhaps better suited for environments where you have, let's say, different organizations or different zones or different environments, but you share a common supervisor cluster, but gives you at least the opportunity to connect those namespaces to a dedicated tier 0 for that environment, organization, or tenant. So there's a lot of improved flexibility and multi-tenancy options here. And then on the namespace level, you can configure a subnet prefix. So say by default, you'll have a supervisor cluster with a /28 subnet prefix. On the namespace level, when you create a namespace, you can override that. And on the right, you see an example in purple where we have specified a /27 subnet prefix because we expect this namespace to require larger subnets. And NSXT in turn takes care of IP allocating that IP and segments to that given namespace. And then 2 additional very important features is that on a namespace level, you can set ingress and egress IP addresses. Again, ingress is all about the service you're going to expose from your namespace to the network. And means that the allocation of load balancers and ingress IPs will be on that level. So when you create a namespace, it gets by default one ingress IP, but you can override the namespace configuration because perhaps that namespace needs to use specific IPs for ingress to make sure there is either traffic engineering and or physical networking, like firewalling on the physical network to be able to filter that traffic as a destination, because there may be some sources on the physical network which need to go through a firewall, but you want to manipulate and ensure that it's being allowed to specific destination, because that destination IP perhaps is associated with a specific networking zone. So you can override in blue, for example, on the left, for a given supervisor cluster, for a given namespace, the ingress IP in order to do some traffic engineering and to route that traffic properly in and out the supervisor cluster. NSX in turn will make sure that when you create services of type load balancer or ingress, in the case of vSphere pods, that IPs will then be allocated from that IP range for that namespace. This is also the case for egress. So there might be a requirement that you have resources on your network which are required to be accessed from a given namespace, but you have separation of zones and you want to make sure that only specific IPs are able to reach those resources. So you might require to do traffic engineering or firewall configuration that a given namespace with a specific source IP can reach those resources either on the internet or your physical network. And overriding on a namespace level on egress CIDR means that you can specify which IP they use, and you can expect to be as a source for filtering on your physical network. At the moment, we have only one shared egress IP. So this example with the /24 subnet on the left is a future state, but at the moment you can have really small CIDRs, even /2032s, to specify an IP dedicated to a namespace. In the future, it may be expected that we can manipulate the allocation of egress to specific resources in a given namespace, but at the moment we use one egress IP for source netting towards the physical network. And in the UI, it looks like when you create a namespace, you give it a name, a description, and you have a little checkbox with override cluster network settings. When you select that, you have a number of options you can override. You don't have to override them all. You can mix and match whatever you need. You can select your tier 0 gateway, your net mode, your load balancer size, of which we are going to talk a bit later as well. And then the namespace network, subnet prefix, ingress and egress ranges. So depending on what you need, like it says, optional, you can specify those settings and create the namespace. What's important to know is you can set egress ranges at namespace creation. You can add ranges after namespace creation, but say you want to recall or revoke a range for ingress or egress, you cannot delete those ranges. So make sure that you're sure what your IP address allocation is right. Otherwise, you perhaps need to recreate a namespace with different settings in order to free that IP range. So again, adding is supported, but removing is not. Take a breath here to talk about security in NSXT in vSphere with Tanzu. So if we talk about security for vSphere with Tanzu with NSXT for namespaces, we talk roughly about two ways to secure workloads in namespaces. First of all is obviously using the distributed firewall and or using capabilities of your CNI inside TKG clusters. And the other one is leveraging the tier 1 gateway north-south firewall capabilities, or a combination of both. By default, in a namespace, we allow traffic to talk to each other but traffic between namespaces is denied. Additionally, by default, ingress and egress traffic on a tier 1 gateway for each namespace is allowed. Obviously, this doesn't mean that you're exposed, because what in Kubernetes workloads, you generally create a service of type load balancer or ingress to expose your application to the outside world. Well, that's for netted topologies. Obviously, if you use routable pods, this would mean that a pod is pingable and is reachable. So you may want to ensure that the security on your namespace is being heightened by either distributed firewall rules and or tier 1 gateway rules. So what you can do is, obviously, you can leverage the tier 1 gateway to secure namespace access. So each namespace gets a dedicated tier 1 gateway. Each namespace can have dedicated north-south firewall rules on the distributed firewall or on the tier 1 gateway. And this means that you can set, let's say, roughly a deny on the tier 1 gateway and only expose inbound ports for namespace access to secure access, only to be allowed on a specific port into a namespace, after which you can create workloads in a namespace and create a load balancer, for example, to expose, let's say, HTTPS to the outside world to be able to reach that application. You can then use, in case of vSphere pods, the distributed firewall capabilities, or using TKG clusters, let's say by default Entrea as a CNI to secure the pods inside your TKG cluster. There are some caveats here, because when you create a tier 1 gateway and when you want to secure inbound access in a namespace on the tier 1 gateway, we need to consider that we require obviously 6443 API, Kubernetes API access inbound, because when you create a TKG cluster, you need to be able to access it through the Kubernetes API. Also, traffic from the system namespace, which is connected to the supervisor control nodes, will be sourced from a 10.244.0.0 network by default. So that means that you need to allow that traffic as well, because there are some health checks going on towards TKG nodes and vSphere pods. DevOps teams obviously require access to that IP, load balance IP for TKG cluster access. And namespaces may need access to private and public registries or other resources on your physical network or on the internet to work. All right, so make sure those ports are opened. Also consider that ingress traffic are processed by the firewall before being netted, and egress traffic is first processed by the firewall before applying source net rules. And considering the fact that load balancer IPs will be allocated automatically, that can be hard to track, because you cannot do a specific destination IP, because NSXT will allocate that IP automatically. You can, however, specify an IP in a service type load balancer CRD, but that means that you need to track those IPs yourself, and those IPs need to be member of the IP ingress IP ranges you specify on the cluster or namespace level. Whatever you consider to do for security, and we do see customers looking at securing deny by default their namespaces. What's important is that you always review the required ports on ports.vmware.com, because ports may change with versions. And if you look at that site and sort on vSphere Tanzu, you will see all the ports required between control nodes, your workloads, and ports required between for external access inside your cluster. Then look a bit further at the network policies for vSphere pods for both ingress and egress. This is about using the distributed firewall when you create Kubernetes network policies. So in this example, in a namespace, I have pods for Nginx and I have pods for Redis. And in this example, I'm trying to show that you can leverage network policies and apply those to those pods to secure access, ingress, and egress from those pods. So in this case, you only want to allow, for example, 443 to the Nginx pods, and only allow Nginx pods to be able to access the Redis pods. on port, in this case, 6379, which is the default Redis port. And this is just one example, but this you can successfully secure your vSphere pods using native Kubernetes network policies. And those will be exposed as distributed firewall rules and automatically be created as security groups and applied to those workloads in NSXT. Which also means that when you create additional pods with the same labels, they will automatically be added to those security groups, and NSXT enforces that security. For workloads in TKG clusters, you can leverage Entreya by default as a CNI to use network policies, Entreya network policies inside your cluster and to secure those workloads. And with coming versions, you will see further integration between NSXT and Entreya, because you can now apply specific NSXT rules towards Entreya clusters as Entreya cluster network policies. But also Entreya network policies will be visible in NSXT to give you as a network engineer full visibility in what's going on inside a TKG cluster in terms of rules and firewalling. So that's really good for full visibility and security of workloads on NSXT with vSphere with Tanzu. How are we doing with time? 5 minutes left. Oh, 2 minutes left. Okay. I'm running out of time, so I'm going to quickly go about load balancing. So each namespace gets a dedicated load balancer associated with the tier 1 gateway. That means that traffic through that load balancer instance will be shared among resources. So if you have multiple TKG clusters or different vSphere pods leveraging the same load balancer, that traffic will be shared on the load balancer on the tier 1, attached to the tier 1 gateway for that given namespace. And by default, it's a small load balancer instance. And in vSphere 703, you can even choose a different size on a namespace level. For TKG clusters, when you create a service of type load balancer inside a TKG cluster, what happens is that the worker nodes expose the services on the node port, and the external IP will be allocated by NSXT and will be instantiated as a virtual server attached to the load balancer on the tier 1 gateway of that namespace. And the TKG nodes will be identified using the IP, and in this case, they are identified by the pods IP you could configure. And those will be added as members of the server pool. Again, in terms of performance and scale, they share load balancer resources. By default, it's small. You can select the size, but selecting a size from vSphere 703, which is supported, will have some important considerations in terms of scale. And what I mean by that is that by default, you have a small load balancer. This means that on a large edge node, you can have up to 40 small load balancer instances. And that means in an edge cluster with maximum of 10 edge nodes, you can have up to 400 instances. But those instances are obviously active standby. So that means that you can have up to 200 load balancers. You need at least one load balancer for the system namespace. So you have 199 small load balancer slots left in your edge cluster for your namespaces. So I hope this makes sense with this diagram, because if you select a medium or large size load balancer, they will take more space in a given edge node. So in this example, a large edge node with a large small load balancer, that large load balancer will require a dedicated edge by itself. So what about scale? Well, you can either scale out and scale up. You can scale out by adding edge nodes to your edge cluster. So a maximum of 10 edge nodes is currently supported. You can obviously create multiple supervisor cluster with multiple edge clusters, but you can also scale up by creating a larger size edge node, extra large, or even a bare metal edge node. And that will have a lot more resources for load balancing. So this is all about, determining the size requirements of scale for your deployments and scale out or scale up as needed when the workloads are being created in your supervisor cluster. So considering time, I will stop here. And I'm open for questions. So if you have questions, put them in the chat or open your mic. I'm very happy to answer them. There is an additional content of edge clusters, which I will share when this deck is being shared on the VMAC platform. So if there are questions, please let me know. And otherwise, thanks for attending, and I hope it was useful. If there's a survey, please fill in the survey and let me know what you think, and have a good holidays.